This video will entail an introduction to databases and data management, and mainly the databases part. So the data management is not discussed here yet, which will entail both Git, which is a tool that we use to basically store our code and to keep version control of our code, and also fair data management, something about GDPR a little bit as well, data management plans. But in this one, we will focus on the databases part. So in general, during BIT04, what will we see? Well, this introduction, of course, but also MySQL with everything you can do within MySQL, specifically MariaDB. On the other hand, we will also see NoSQL, which is mainly MongoDB that we will be discussing, and that will be inserting, updating, finding, and so on. So everything you can do there as well. We will also have a small part about the online databases in bioinformatics. So we know already a lot of databases, NCBI, for example, UCSC, and you will see a lot of other ones during the program. And finally, a lot of databases already exist. For example, NCBI, Ensemble, and so on. So we want to also be able to interact with it programmatically, yeah, and that we can often do via an API. For example, a REST API is one specific type of such an API. This last part I already discussed, so these are the main data management things that we will discuss in BIT04. For the course itself, we have slides. There's also a syllabus that is in progress, not entirely finished so far, or maybe by time of the video that you watch it, it might be finished. And the exam exists out of theoretical and practical part. If you want to have more info, you can always check the course unit details. So the introduction itself. Um, just to give you an idea, why do we need databases? Well, we get more and more data. That's of course because our computers get faster. The number of transistors doubles every 2 years. Is Moore's law, a very known law in computer science. It's not an actual law, but something they found out that if they put it on a graph, it looks something like this. So it's nice and steadily climbing. And yeah, the size of these transistors that are in our CPUs, they get smaller and smaller, and computers get faster and faster. So 2 nanometer chip, yeah. On the other hand, yeah, the data itself, storage, becomes cheaper. So, for example, I checked it not too long ago, 20 terabytes of data, $360 is very cheap per gigabyte. Of course, it's a hard drive, not an SSD or anything, but still a lot of data for relatively cheap. Also, very big SSD cards are available. And also, just in general, the technology is getting cheaper as well. The Human Genome Project and the first human genome, to put it together, it cost 3 billion US dollars. Often nowadays they use Illumina, which costs about 1,000 US dollars for one human genome. And if we check, for example, using Nanopore, about $208 at the time of this recording. So very cheap to basically produce a lot of data. So this is a bit the conclusion of these first slides. Speed to produce data goes up, and the cost to produce and store data, that goes down. So we get more and more data. We want to store it somewhere, and that is where our databases come in. You have two types of data. On the one hand, you have structured data, which is the typical spreadsheets that you might think of, Excel files, CSV files, and so on. Can be every type of data, numbers, dates, and strings. But you can see that actually only a small part of enterprise data is structured, 20%, versus the 80% that is unstructured. And unstructured data, that is what you cannot nicely place in a table, or maybe there are fields missing, and so on. Typical examples here are just files that are not nice text data, for example, images, audio files, video files. Everything from Excel actually up until PowerPoint and so on. So Excel, you might think, nice tables, but the Excel format itself, is not just text. There is a lot of other data in those Excel files as well. The bottom part is less important, so less storage versus more, and easier to protect versus a bit harder. Then we get to what is a database actually. Database is basically just a program or some multiple things that work together where we can store some information. Read data. Data can be anything, numbers, dates, text, what else you have in here. Can also be images, files, and so on. But in the end, we want to have some sort of structured storage of that data. Even if it's files, maybe organize them in a intelligent way that you can easily find them and so on. Can also be an example of that. We also want to efficiently interact with the data, meaning, if I go to a website, I don't want to wait minutes before my login has been verified and so on. And a database, basically has to allow the CRUD, which is an acronym for create, read, update, and delete. So you have to be able to create data. If you create data, often you want to retrieve it as well. So reading the data, you might have made a mistake or something has changed. So we want to update it then, and maybe we might want to delete some data also. So deleting. CRUD, very known in databases. And databases, they are used everywhere. So just a small section. Websites, every website you go to almost has a database behind it. Not all of them, but most of them. Any warehouses, for example, have a lot of databases, not only of the products, but also what do the customers buy and so on. How can we make intelligent, what do we call it, marketing for those customers? And even you are using databases. So also files on your system are stored in some form of database that we can easily retrieve data and files and so on from our computer, smartphones, and so on. Of course, if you use Facebook or any other social media, you're also using databases. In research, however, which is a bit more interesting for us, bioinformatics, we have a lot of them. Here are only a few. Ensemble, UCSC, and CBI is not even on here. ENCODE projects, 1000 genome projects. So you can see that basically we have lots of different types of data, not only data, but also types of data that we need to store. For example, sequences, but also annotations, and also, for example, experimental data that we find. So that's why we really need it within bioinformatics. When you think about a database, you might think that it's just some sort of software that reads some data and so on, but that is actually not the case. So a database system in the whole has basically four major components. One of them is, of course, the users. If there are no users, then it's just some data that is stored somewhere, but then you don't really have a database. You need to be able to interact with it, and not only you, but for example, also other programs can interact with it. So that is quite an important part. The second important part is, of course, the hardware. Where is the data stored? On a server, on a laptop. For us, it will be our laptop. But in companies, most of the time, this is, of course, stored on some sort of server that is always reachable. Another important component, I will jump to the middle, is actually the data. So the data itself, it's just some file or something that is on the hard drive. And basically on its own, it does nothing. It just sits there. And that's what I meant. You need all those components to be able to talk about a database system. So the data is, of course, what we want to retrieve and so on. And to retrieve it, it's on some sort of server. Then you have the data itself. To retrieve it, you need some sort of software in between that will get you the data, but also let you insert new data, delete, update. So the CRUD command, basically. To go in a bit more detail, so if we check here, so users, there are two major components here. So users, it's also other programs. The one is authentication. Authentication is basically saying, who are you? So basically logging in to a database, username, password, and so on. That's manually, of course, but you can also do this programmatically and provide the email address and password or username and password. That can all be done. Another way, often also used when you automate things, is to create some API token. It doesn't have to be an API token, it can just be a other token, personal access token, or things like that. But some way of saying who are you, and in the second step, then authorization. What are you allowed to do? So the administrator can, of course, do a lot more than just a normal user. And maybe a normal user should only be able to look at the data, but not update it, delete it, insert new data. Maybe that's not allowed. So authorization is basically saying, what are you allowed to do? Then the hardware, yeah, hardware exists out of several things, processor, memory, things like that, and can be just a laptop, but can also be an entire server or even a cluster, which is basically multiple servers working together. Imagine if you go to Facebook and everything is in one server, yeah, then it will be quite slow. So there they will do tricks to basically split it up over multiple servers that work together. The software component, yeah, the most important one here is the database management system, or DBMS. And that's basically just the software that you use to store, retrieve, manipulate, which is creating and updating, also deleting all the data. Yeah. So it's one of the components. Yeah, there are other ones to see how is my database doing, is it not overloaded, and so on. That will not be the database management system, but some other program. Yeah. But for us, this is the most important one. This is the one that actually interacts with your data. Finally, we have also the data. You will have to need, or you will need some structure in your data still, even if it's unstructured, because otherwise, yeah, also NoSQL systems, which we'll see, which are less structured, would also not be able to find anything in your data. So needs to be somewhat structured as well. Little redundancy, meaning, yeah, don't copy your data too much. If it's one time in there, that's often enough. You don't need to store it 15 times. And for this, we have tricks like normalization and so on. But this is more optional. You will see that in NoSQL systems, this is often not really looked after because we will just store it multiple times. And then also, is it shared or not? So as one user using it, are multiple users using your database is also quite important. Yeah. Who can access what data and so on. Bit coupling back to the authorization part. Within a database, or a database management system, we have a concept called data abstraction. Basically, it's just different levels of what is my database management system doing. Yeah, and the one that we often know is the view level. So this is what we will see when we ask the database management system to return us some data or to store some data. We will have a view from the database saying, this is in here, and things like that. Yeah. And multiple users can have different views, and your Facebook will not look the same as mine, basically. And so those views are, can be different. Can also be the same. If you go to a website where you don't have to log in, but with the database, we go to the same website, we will see the same, for example. The physical level is the bottom level, basically, is actually really where is my data stored? Where on the hard drive is it? On which server is it? On which laptop is it? And then where exactly? And so the exact location, memory location, and so on. In between, you have the logical level, which is basically saying, okay, I know there are zeros and ones on this hard drive, but the logical level will say, so those zeros and ones, those are actually numbers, and those other ones, those are text. So it's in between. what fields, attributes is stored in here. So if we go back then to what is such a database management system, it's a computer software application, so just a program that's running. It interacts with basically all the other components of a database. So this is the software component. This interacts with the data, the hardware, the users. And it also shields us from all that information. We don't need to know on which server and at what exact address in memory it is stored. We just want to have the data. And as mentioned, it's the most important software component, but not the only one. And it does basically all the stuff we said before. So the CRUD commands and saying who are you and what are you allowed to do. So what makes a good database management system? Well, that's a bit up for debate, of course, but in general, these are some rules that often are viewed as this could be a good database system, database management system, I should say. It should have enough storage. That's more your server and so on than the system itself, but you should have enough storage. It should be easily accessible, that everyone can use it easily, and it's not super difficult to get access to data and so on. So it's a bit logical. It should also be secured. So this is a bit the authentication and authorization part. And of course, the CRUD commands, it has to be able to do those. Otherwise, it's not really usable. Often we also want to check if we insert something into the database that the data is correct. If I say, here is the birthday of people, and somebody says yellow, because they filled in the wrong field, favorite color, for example, and they accidentally fill it in the birthday, we should be able to check this also using the database management system. Preferably, it's also quite quick. Think about the Facebook example. I don't want to be waiting minutes before I load my page that I get all the data. I want to have it fast, and the faster, the better. Little redundancy I already mentioned, but this is again dependent on application and also the database system that you use. MongoDB will have redundancy, and preferably we also want to have it as a clear structure, so that it's not too difficult to use. Here are some examples of such softwares that we can use. So you can see SQL systems, MySQL, MariaDB, Postgres are all examples. Currently, MySQL and Oracle are at the top. After that, Postgres is in the list of most used database systems. Microsoft Access, you maybe used some time in the past, but we will actually be using MariaDB, which is basically an open source version of the MySQL. There are some differences, but they are very interchangeable, so you can easily swap them out. These are SQL systems. It's one part of systems, the first one that we will be discussing, and more info will come when we discuss MariaDB. You also have NoSQL systems. This is when your data often is a bit less structured. Then we will often more use NoSQL systems. Also here, lots of examples: Neo4j, MongoDB, Redis, Elasticsearch, CouchDB is also an example of NoSQL systems. Here we will discuss MongoDB. There is a third kind of systems, which are called new SQL systems. So as you can imagine, SQL systems have their advantages. NoSQL systems have their advantages, but each might also have some drawbacks. These new SQL systems try to combine the best of both worlds. Some examples are Couchbase and VaultDB, but for so far as I know, they are a bit lacking behind in usage. So not a lot of people are actually using these systems yet. Maybe in the future, this will get a sudden surge in usage. But for now, we will ignore these new SQL systems and we'll focus on SQL MariaDB, and NoSQL MongoDB, which is basically the most used NoSQL system out there. So we talked about database management systems. We also talked a bit about the levels of abstractions in these database systems. But now we will talk about the data models. So the data model is basically how is my data structured, what is in there, and so on. So it's independent of any program that you use, so independent if you use MariaDB or MongoDB or whatever. It's basically just thinking about the data itself. The first level in here is the conceptual data model. Conceptual meaning that it's a concept, it's not fixed in any way. And the conceptual data model is just saying, okay, I have some data. Which things do I want to have in my database? Which ones can I throw out? And at the end, what kind of data do I want in my database? There is an example here on the right. Imagine that you are a store, you have some customers, and you want to store their name, address, gender, birthday, GDPR compliant, of course. But imagine that this is GDPR compliant. Then this is the information we want to store about our customer. You can say, okay, I also have some products, so I also want to be able to store those. Name, how many are there in my store, what is the price currently, and each product might also have a supplier. Think about Nutella. The supplier is Ferrero Rocher, and they are located in Italy somewhere probably. So this is the data I want to store. Not more, not less. Once you've done that, then you can think about, okay, that's the data I want to store. How do I want to store it? How should it look like? Okay, a customer, his name, that will be text. His address also, his birthday, that's a date. So that's not text. It's also not really a number. So I want to store it as a date. Other examples, the stock, I can have 5 pots of Nutella in my store. So 5, but not 5.5. So this will have to be an integer. And the price, I don't know the price currently, but it will be some floating point number. So I want to store it as a float. Here, that's what you can see. Not only thinking about, okay, but what is it actually? Is it text or a number or a date? But also thinking about how do they relate to one another. For example, a customer, he will probably buy multiple products. And a product, probably, it's not always the same customer that buys a Nutella. And there will be multiple customers that buy Nutella. So it goes in 2 ways. A customer can buy multiple products, and a product can also be bought by multiple customers. And this relation in between, because we have a relation between the two, this is then here in a separate table. So some customer with ID 12, ID 12 is John, for example, will buy a product with ID 75. 75 is my Nutella. And he buys 2 pots of Nutella at a specific date. So you get an extra table in between there because you want to have the relation between the two. And of course, to be able to know who buys what, you need to have basically a link to the other tables. Customer ID points to the customer table where you will also have an ID. Person 15, person 15 here. That's what we mean with foreign keys. A primary key is also identified, basically meaning that based on this specific value, we will only have one row in our data. A customer with ID 5, we will not have another customer with ID 5. If we know it's 5, then we know it's this person. And this is where also the normalization step comes in to determine how this all comes together. that we do through normalization, which is also a concept that will be explained later. Once you have done all that, you get this kind of structure. We go to the physical data model, and in the physical data model, this is actually thinking, okay, I know how my data will look like once I put it in the database. Based on all my database systems that I have available, I can now pick one. For example, I will pick MariaDB. And then for the physical data model, you think about, okay, but in MariaDB, you don't actually have strings. No, in MariaDB, it's, for example, a varchar with a length of 45. So really dependent on what is my database system. You cannot do this step if you don't know it will be in MariaDB or it will be in MongoDB. No, you need to know before. And of course, then the server that you will run it on and so on. But the main important thing here is that you will really settle down on, I will use this data type and so on. So that's the data model, structure of the data. You can also have the database model. Database model is basically how does my database look like. So now we're not thinking about the data itself, but thinking about how is my data structured. A simple example is a flat model. It's just, for example, a CSV file. You have some columns, some rows. So a single two-dimensional array of data elements. For example, a spreadsheet, a CSV file, a single sheet, and an Excel file. But remember, Excel files, they are more than just text. And there's other information, the color of a cell, and so on. So here we're just thinking about the text. In a hierarchical model, then you have something like this. Think about your file system. You start at the root of Linux, then you have the home folder, then you have the guest folder, and so on. And at the end, you have some files, but also in your root, you could have some files, or in the home folder, you could get some files. So that's a hierarchical model, so a tree-like structure. One parent, multiple children. In the root, you have guest home, but also slash srv, slash bin, and so on. In a network database model, it's very similar, except that sometimes you can have multiple parents per node. For example, C4 has both B1 and B2 as a parent and has D4 as a child. The main idea I think about when thinking about such a structure is that you have a link here in the dark that points also to the dark and blues. So here you will have a link that points to here. So then here you will have basically two parents, this dark, but also this dark. So think about just symlinks, ln minus s in Linux, and then you basically have some sort of simple network database model. Then we get to relational database models. In the relational database models, we basically have multiple of these flat models, these spreadsheets basically. And for example, here we have an employee. The employee has some data. So he has a manager and he has a year that he started in, year of service, for example. And you have this in two separate tables. These tables does have a relationship. The employee has employee data, so there is some sort of relationship between the two, and we can basically link it back, same as we did here. If we have the customer ID, then we can find out which customer it is. Same here, we have an employee ID, and based on that, we can get his data, because here it will just say 15, and then manager ID is 3, and then year of service is 2020, for example. And this is what MySQL, also MariaDB, will be using. Then you have some special kinds, object relational, where you just don't just have a table, but this table is actually an object, and an object creates an instance. So it's a bit, towards the, how should I say it, object-oriented programming like, But this is a step between. because you can still have relations between multiple things as well. And then you have the final object-oriented model, where you basically just have one big object with all the data. And then you have multiple instances of such object. The instance is then the data, and the object itself is basically saying, what is it? It's the name, it's a date, and so on. An example of such object-oriented model is a document-oriented database. So this is a subclass, you could say, of object-oriented models. And in document-oriented databases, you store things in documents. Documents are then the objects and the instances actually. And those can be in different shapes and formats. So XML, YAML, JSON, BASIC. And an example of that is MongoDB. So the other database system besides the SQL systems that we will be using. So this is almost always NoSQL. And you can see an example here. So it's just a JSON file in this case, where you have some key with a value. So the first name is Bob, the address is his address, and then his hobby is sailing. And then you have a second document, second pair of curly brackets, saying the first name is Gene, address is this again. And you see there is no hobby in here because that's not always required. Depends on the database management system, but in MongoDB, this would be perfectly fine. And one person has a hobby, another doesn't, or maybe didn't fill it in on the website. So then it's empty. Since we start with SQL systems, the relational database models does. So if I go back a few slides, this one here, the MySQL MariaDB one, let's zoom in on that to start. I always say, think about an Excel. You have multiple sheets, and then there can be different data on different sheets. So it's two-dimensional. You have columns, you have the rows. The columns are basically the things that you are interested in, the name, the address, the city, and so on. And the rows are actually your data. So, for example, here, Anderson Roger David, he lives in Miami, and then someone else, Nicholas Paul, lives in Orlando. So rows are the data, columns are basically the fields that you are interested in. If you think about an Excel, you can add and remove columns, but you do that for everything. So if I add in a column between name and address, then everyone gets an extra column. So you cannot say, I will do this for one person and not for another. You're always stuck with the same amount of columns. Of course, if you go to a different sheet, there you can have different columns, different names, and so on. So relational database, I already mentioned it. They have tables, which are just the entities and the things that you're interested in. And they can have relationships. Think about customers, products, and they buy something or multiple things. That's the relationship between the two. So entities, it's again mentioned here, customers, products, the relationship is the sale, the order, however you want to call it. This is just an example to show you what a database could be. So here on the left, you basically see what you are familiar with in Excel. On the right is what you would see in a database system. So you can see it's actually very similar. The data is different, of course, but very similar looking. And the database management systems, remember that's the software that we will be using. If it's for a relational database management system or a relational database, then we call it Relational Database Management System, RDBMS. And those get some extra rules on top of the nice to haves. So you're only relational if you enforce data integrity, meaning if I say you have to type the age of a person in full, you actually type 13, THIRTEEN, then yeah, you have to do it everywhere. Yeah, you cannot say, for the next person that was annoying, now I will write it as a number, 1, 3. No, you have to write it in full again. Yeah. And then it's of course important to think when you start creating the database, should I store it as a number or as text? Yeah. But that's basically making sure that your database management system can check, are you doing it correctly or not? And the other one is, yeah, referential integrity. What do we mean with this? Yeah, a relation between two tables. Yeah, this has to be fixed. You cannot say, again, if I have in one table something in text and another in a number, yeah, then you cannot link them together. So this will make sure that everything is nice. There are constraints. That you have to have a connection between two tables or not, things like that. And basically, because yeah, these are specific things for such database systems, there is one Edgar F. Cott, yeah, interesting person. You should look him up. He studied mathematics and chemistry, I think, and then he was pilot in the Second World War, and so on. And then he did programming, and then yeah, he came up with database systems, especially the relational ones. And he also set up some rules for them to make sure that if you want to have a relational database management system, then make sure that those 12 rules are correct. And then if those are all fulfilled, then you can call yourself an RDBMS. So it's called Code's 12 rules, but actually it's 13 rules because yeah, he was a real programmer at the end, and he just started counting from 0. So you have rule 0, 1, up until 12. So in total, you have 13 rules. Good. Here are some examples of such RDBMSs. Commercial ones. So if you have a lot of money, you can use Oracle, which is the most popular one. There are also some other ones like DB2 from IBM, and Microsoft has its own server. Oracle has also the free version, the MySQL database, and the open source one, community-based, is MariaDB, the one that we will be using. Since we, as bioinformaticians, we like open source, we will support MariaDB. And basically, they are almost interchangeable. Some small things here and there that are not entirely, but in 99% of cases, we can just swap them. Another one was the Postgres, PostgreSQL, but to just say Postgres. And SQLite is an interesting one because SQLite is basically, yeah, it's not storing it really in, yeah, how should I say it, a separate database directory or something which is closed off from users and so on. No, SQLite basically just stores it in files that you can also edit and so on. So that's quite nice, also used a lot on the web. So that brings us to the end of this first introduction video, where we just discussed the different kinds of technologies. And as mentioned, we will now look further into MariaDB and MongoDB during this course.